Hello friends, this is the 11th video of capacitance, particularly related to loss in capacitors. While solving some problems, we should deal with Kirchhoff's laws in in capacitance. If you use the law and its principle, I think some technical problems may be solved easily. Okay, there are mainly two rules. First rule is gives the charge conservation, whereas the second rule is the energy conservation. Okay, now the first rule or first law, at the junction, at any junction, algebraic sum of charges I equal to 1 to n, that equal to 0. Sum of in an isolated system, net charge remains the same. It is its meaning. At the junction, sum of charges equal to 0. That means some charges entering towards the junction and some charges leaving towards the junction. If you add all are 0. Now, to explain the law, you can take some charges as positive, some charges as negative, but as such, charge as per the principle of capacitor, some charge are plus, some charge are minus. Now, let us take, this is the example, a junction. You take in this figure, O is the junction, this is one capacitor. Here charge plus Q minus Q enters the junction. Then after that minus Q charge comes to the junction along one direction. Suppose charge flows, this is plus, and another direction charge is again plus, so this is minus minus. Now, as per the law, the junction is directly connected to the three plates of the charge. Three plates, that is first capacitor right plate and second, third capacitors first plate. Now, this shows that total charge means minus Q entering towards the junction O equal to total charge means plus Q1 and plus Q2 leaving the junction. Okay, if you use this loop as per the system, minus Q plus Q1 plus Q2 must be equal to 0, or you write Q1 plus Q2 equal to 0, that equal to Q. Therefore, you write sum over charge entering, that equal to sum over charge leaving the junction. Okay, sum over charge entering the junction is exactly equal to sum over the charge leaving the junction. With the help of this formula, you can find out in which conductor, in which capacitor particularly, what charge is flowing. Okay. Now, let us discuss about the second law. Second law states that in a closed circuit, sum over potential is equal to 0. This is the law. Total potential, algebraic sum of potential in a closed circuit is equal to 0. Okay. Now, to explain this system, you can assume two assumption you can take. This is a convention. The first convention is along your direction if current flows and you are moving along this direction, then you can take E is positive. That means EMF is taken as positive if it moves from negative terminal to positive terminal along your direction. Okay, your direction, that is important. Then here another is, that means capacitance, if it moves from negative plates to positive plates, if it moves from negative plate to positive plates, that is you can take V equal to Q divided by C, okay, that equal to positive, and this is taken as potential rise. This is taken as a potential rise. That means any potential rise, V is taken as positive. If charge flows from plus to minus, that is a potential drop. That means capacitor stores charge, the potential decreases. In that case, you can take it as a negative. Okay, any potential drop is negative and any potential rise is positive. Now, these are the two conventions one can use while solving this Kirchhoff's law. Now, this is your example. One example, you give the names, that is this is C1, C2, C3, that is C4 and C5. Sorry, this is a cell C5, that is 4 capacitors are there. You put this junction is A, this junction is B, this junction is C, and that junction is D. Then you take E, then you take F, A, B, C, D, E, F. Okay. Now, let us take cell E1 provides charge Q1, whereas cell E2 provides charge Q2. Both the two cells, they provide charge Q1 and Q2. Come to this point, that is Q2. Q2 here, this is plus, means this is minus, Q2 is moving, this is you take plus, this is minus, this is Q2. Then come to this side, this is plus, this is minus, this is Q1 along this direction, this is plus of Q1 plus Q2, this is plus, because at the junction C, the total negative charge must be equal to, at the junction D, total negative charge minus Q1 minus Q2, I am writing Q2 here, minus Q1 minus Q2 must be equal to Q1 plus Q2, because at the junction D, net charge 0, junction A net charge 0, junction B net charge 0, junction C, E, F net charge is 0. You can use this type of a principle. Then Q1 plus Q2, this is a minus, that comes to this side, then Q1 goes to this side and Q2 along this side. Okay, that means this is Q1 minus, this one is, that is, this is plus means minus, this is minus and this is plus. Okay, so this is plus. Okay, again this is a junction, plus equal to minus, plus equal to minus, therefore this is minus is connected to E. Therefore, at any junction there must be some negative charge, there must be some positive charge. If you add all the charges, algebraic sum is 0. So, this is all about your, that is Kirchhoff's second law, current distribution. Okay. Now, let us use this assumption. You can use this assumption. By using this assumption, let us write an equation. You use loop rule A, B, C, D, A. This is a loop. I am taking A, B, C, D, A. You take loop rule A, B, C, D, A. Okay. Now in the loop rule A, B, C, D, A, that is you start from A, that is charge is moving from plus to minus. Okay. Charge is moving from plus to minus. Here minus to plus is positive in capacitor, plus to minus is negative. Therefore you take minus Q1 by C5, then come to E. It is plus to negative to positive, negative to positive, negative to positive. So this is plus E1. You start from A, come to B, next come to C, then come to the point C to D. See, from C to D, again charge flows from plus to minus, but here minus to plus is plus. Therefore this is again minus Q1 divided by C2, Q1 by C2, then comes to the last junction, that is D to A. D to A again plus to minus. Therefore this is minus Q1 plus Q2 divided by this one is, this is E, C5. This equation is 0. Okay. This equation is 0. Now I am taking the loop along this direction. I am taking the loop along this direction. Okay. A, B, C, D, A. You write and move along your direction. Suppose if another person want to write the loop is along A, D, C, B, A, then what happens? I am marking in black ink. This is blue ink. This is black ink. Now let us start along the direction of black. Okay. If you start from A, then move to D. Okay. If you start from A, then move to D. Then current is, that is opposite to plus to minus your opposite direction. Therefore this term first is Q1 plus Q2 divided by C5. This is positive. Then go to, this is again, that is plus to minus, your direction is opposite to this. So minus of minus, again this is Q1 divided by C2. Then comes to CB. CB, your direction is opposite to E1. Therefore minus E1 is minus. My direction is not. My direction is this. If my direction is this, I take E is negative. If my direction is this, then you take E is positive. Then finally you come to, that is C5. This is again, my direction is minus to plus, but charge is moving from plus to minus. Therefore this is again minus Q1 by C5 equal to 0. Okay. Sorry, this is minus of minus, that is plus. Now if you check these two equations, nothing is changed, same thing. Simply you take minus common from any one, you will get the other one. Okay. Similarly, you can apply, that is either loop rule to, that is the left circuit, closed circuit FADE along anti-clockwise, or FEDA along clockwise. Okay. Now let us use the Kirchhoff's law in two loops. Let us take, this is the first loop. All the capacitors are in microfarad. Voltages are V, 2 microfarad, 4 microfarad, 6 microfarad. They are arranged like this. This is 10 volt and 20 volts. Okay. Now if you imagine battery supplies Q1 charge, that is first battery Q1 charge, and the second battery you can change like this. This is Q2 charge. This is plus Q2 minus, this is plus Q1 minus Q1 minus Q2. So this is plus Q3 equal to Q1 plus Q2. In case of a 6 farad capacitor, Q3 charge moves and Q3 charge must be equal to plus plus. Now this represents a system, this represents an isolated system. That means you can use first junction rules to B, junction rules to A, C, D, E anywhere. Okay, then you take the loop rule. To take the loop rule, any one rule, either clockwise or anti-clockwise. Let us take clockwise. That is A, B, E, F, A. You start from A. We are moving along this direction, but this is plus to minus, this is minus. Here potential is Q1 by 2 microfarad. Then come to B, then come to this minus means this is a plus, this is a minus. Okay, if this is plus, then again minus Q1 plus Q2, Q means Q3 divided by 6, then comes to here, current flows from negative to positive. This is plus 10 volt, that equal to 0. You need not write units. Okay, plus 10 equal to 0. So this is your results. Okay, now if you take the loop, this loop, either this is a clock, you take this is anti-clock, or clockwise, whatever may be, that is, it will be easy if you take along one direction. Okay, so now that is, you start from the loop B, C, D, E, B. Okay, B starts, then comes to this is minus to plus, means this is positive. 4 divided by, Q2 divided by 4 microfarad, then comes to along this is 12 is negative, then comes to this is minus Q1 plus Q2 divided by 6. Our direction is this, but charge is this, so this equal to 0. Okay, so now in the second equation, you take that one is minus 12, two charges are plus, so plus Q1 Q2. Okay, charge is moving from Q1 plus Q2. This is the case. Now these are the equations. Okay, now similarly you can use this loop, write two equations. These are the microfarads. Okay, this is 12 volts, only one cell, this is microfarad. Now this cell provides current, charge Q, only one charge, should say plus Q, then this is minus along this direction, this is minus is coming, this means plus Q2 plus Q3. Okay, that is Q2 plus Q3 must be equal to what? That is Q1. You take this is Q1, then Q2 is, this is minus. Okay, this is minus plus, then Q2 is plus minus, this is. Okay, so now these are the charge flows across the junctions. Okay, charge flows across the junctions. Similarly, you take one circuit A, B, C, D, A, another is C, A, B, D, C. Use either clockwise or anti-clockwise the assumptions, write any equations, then you get the values. Here you write Q1 equal to Q2 plus Q3. So therefore practically there are two unknowns, Q2 and Q3, therefore you take two loops. Wherever Q1 comes, you put Q2 and Q3, then solve it. Another question is, if suppose I am giving capital A, capital B, capital C, capital D, but here I am writing small a, small b, why? Suppose it is asking what is the potential depth drop across BAB. If the question asks an additional question, if it asks what is the potential difference across any one arm, I am taking one arm as a AB. Now along that arm the charge moving is Q2. Okay, so BAB is what? if you get Q2, then Q2 divided by 4 microfarad if you put, then this is your answer. Okay, this is your answer. So in this way you can calculate charge in each and every branch. Then if a particular charge flows across any branch, what is the potential difference across that branch, you can calculate also, and you can compare the potential across one branch to another branch if they are connected in series or parallel. Okay, so I think these two laws particularly will give you immense help to find out the charge distribution or potential across any branch. Okay, thank you. If you like this video, like it, comment it.